Hey everyone! So today we're jumping into the world of chemical shorthand. In organic chemistry, molecules can get really big, really complicated really fast. And trying to draw out every single atom and bond, it's a lot of work. So how do chemists draw these massive structures in a way that's both quick and clear? Well, that's what we're here to figure out. So here's what we're going to cover. First, we'll talk about why drawing everything out is a problem. Then, we'll look at the first fix, called condensed structures, before moving on to the ultimate shortcut, skeletal structures. After that, we'll get into how we can add meaning by finding the most important parts of a molecule, and we'll finish up by talking about why it's so important to pick the right kind of drawing for the right situation. All right, so let's start with the challenge itself. When you're dealing with organic molecules, you're often looking at dozens, maybe even hundreds of atoms. If you had to draw every single one of them in full detail, every carbon, every hydrogen, every bond, it wouldn't just be annoying, it would be a huge waste of time. I mean, just look at this. This is cyclohexane drawn out in its full Lewis structure. Yeah, it's accurate, but it is so cluttered. Can you imagine drawing this over and over again for your notes or for a reaction? The really important part, that 6-carbon ring, it's almost completely lost in all that visual noise. Yeah, just looking at that is exhausting, right? It just makes you think there has to be a better way to do this. And you'd be right. Of course there is. So let's check out the very first step chemists took to start cleaning things up. So, our first stop on the road to simplification is the condensed structure. You can think of this as like level 1 of chemical shorthand. It's a way to simplify the drawing and make it a whole lot easier to write out, especially if you're typing it in a line of text, but without completely erasing all the atomic info. So what does that actually mean? Well, a condensed structure still shows every single atom in the molecule, but you just leave out the lines for the bonds and any lone pairs of electrons. Just that simple little change makes the whole thing look so much cleaner and makes it way easier to read and write. The main idea here is really simple. All you do is group the hydrogen atoms together with the carbon atom they're attached to. So a carbon at the end of a chain that has 3 hydrogens, that just becomes CH3. A carbon stuck in the middle with 2 hydrogens, that's CH2. See, it's pretty straightforward. And we can actually take this a step further to make it even cleaner. If you have a chunk that repeats, say a bunch of CH2 groups all in a row, you can just group them together in parentheses with a little number to say how many there are. And check this out, it's also a super clever way to handle branches. You just pop the branch into parentheses right after the carbon it's hanging off of. Okay, now it's your turn to try this out. On the screen is a Lewis structure. Go ahead and pause the explainer for a second and try to write out its condensed structure using the rules we just went over. Go on, give it a shot. Okay, you back? How'd it go? The first pass is just grouping all the hydrogens with their carbons, which gives you CH3, CH2, CH2, OCH2Cl. But we can make that even better. See those 2 CH2 groups next to each other? We can condense that part to CH3, CH2, 2, OCH2Cl. It's just a much neater, tidier way to write the exact same molecule. Condensed structures are a great start, for sure. But now it's time for the main event. We're talking about skeletal structures. This is, hands down, the fastest, the cleanest, and the most common way that organic chemists draw molecules. This is how you really start drawing like a pro. The beauty of skeletal structures is that they're based on just a few simple rules. First, you just assume there's a carbon atom at any corner or at the end of any line. Second, you don't even draw the hydrogens that are attached to carbons. You just assume that each carbon has enough hydrogens to give it a total of 4 bonds. And third, any atom that is not a carbon, what we call a heteroatom, you have to draw it in along with any hydrogens attached directly to it. And this is the magic right here. Remember that messy drawing of cyclohexane from the beginning? Look at it now. On the left, you've got the cluttered Lewis structure, and on the right, the skeletal structure. It's just a simple, clean hexagon. That's it. All of that information perfectly captured in just 6 little lines. It's so efficient. Okay, so what happens when a molecule isn't just carbon and hydrogen? Easy. Take a look at cyclopentanol here. We draw the 5-carbon ring as a pentagon, and for the oxygen and its hydrogen, that OH group, we just write it in. This follows that third rule perfectly. You always have to show the heteroatoms. Okay, so we've pretty much nailed how to draw molecules efficiently. So now, let's switch gears a little bit from drawing them to actually understanding them. And the key to that is learning how to spot the most interesting, most reactive part of a molecule, which chemists call the functional group. So, a functional group is basically the reactive center of an organic molecule. It's a specific little arrangement of atoms that gives the whole molecule its unique chemical personality. It dictates how it's going to behave. It really is where all the chemistry happens. And to help us focus on this reactive center, chemists use another great little piece of shorthand, the letter R. You can think of R as just a generic placeholder for the rest of the molecule. The carbon and hydrogen backbone that's usually not as reactive. This lets us just zoom right in on the functional group itself. Let's make this real with an example we all know, ethanol. The carbon backbone part is the CH3CH2. We can just call that whole thing R. The important reactive part is that negative OH group, which is called a hydroxyl group. So we can just think of ethanol as ROH. That structure, that functional group, is what makes ethanol an alcohol. Now, there are a ton of functional groups out there, but we can make them easier to learn by sorting them into a few categories. For the most part, they fall into three main types: hydrocarbons that have carbon-carbon double or triple bonds, compounds with a single bond to a heteroatom, like that oxygen we saw in the alcohol, and compounds that have a carbon-oxygen double bond, which is called a carbonyl group. So we have gone all the way from these super detailed drawings to these really elegant shortcuts. And that brings us to our final and maybe our most important point: understanding why we even have all these different methods and knowing when to use each one. It really is all about choosing the right tool for the right job. This table pretty much sums it all up. Your classic Lewis structure gives you the absolute most detail. It's perfect for when you need to see every single electron, like if you're trying to figure out how a reaction works. The condensed structure is that nice middle ground. It's awesome for quickly typing out a chemical formula in a sentence. And then you have the skeletal structure. It has the least amount of explicit detail, but it's by far the best for quickly seeing a molecule's shape and spotting those all-important functional groups. We've seen just how powerful and clean skeletal structures are. But like we said, it's about picking the right tool. So I'm going to leave you with a question to think about. When might that super cluttered, fully detailed Lewis structure actually be more useful, maybe even essential, than its elegant skeletal cousin? Thinking about that will really help you understand why all of these drawing styles are a vital part of every chemist's toolkit. Thanks for tuning in.